All right, good morning, everybody, and thank you for coming this morning. This is a great turnout. We were not sure how many to expect, especially on a relatively short planning cycle on this one. So thank you for coming, and you're gonna hear a little bit more about the program in a bit. But I think many of you may be wondering, who is Kairos Regina? Who is this group that is suddenly offering this workshop? So I just wanted to say a little bit about that. So there's a national ecumenical justice initiative called Kairos Canada, which is a coalition of Canadian churches that have been engaged in justice work for something around 40 to 50 years now, in a variety of different ways, and they're involved with some overseas development projects as well as Canadian justice projects. There are also local affiliates, and that's what Kairos Regina is. It's a local affiliate of the national organization. Here in Regina, we have focused on climate issues, and we've done a number of things over the years. We've been focusing in climate for about 4 or 5 years. Was it about a year and a half ago, or a year ago? We had a workshop called Creation Care in Our Places of Prayer, and you can find this brochure up here. This is some of the reflections from that, about that if you're interested. That was a focus on helping churches and other faith communities to green their buildings. This event is intended to be more broadly focused on particularly housing, and you're going to hear about that one a little bit more from the speakers, so I shall not say more. Kairos Regina, though, we do have a registration list here. If you'd like to give us your email, we will send you notices of other events in the future. Thanks a lot. And Kathy Cameron will take over.
Thanks for pulling this together.
Hi, I'm not as confident as Nick, so I have everything written down.
Can you stand by this microphone?
Oh, by the mic, sorry. So my name is Kathy Cameron, and I'm part of the Kairos Regina group. And on behalf of our team, I would really, again, welcome you today. And thank you for braving the cold to be with us. We hope that you will leave today with a good understanding of how heat pumps work and why they are a viable option in our province as an alternative to heating exclusively with fossil fuel. The approximate time of the presentation itself will be about an hour, and then after that we will have a time for question and answer. We anticipate about half an hour for that, but we are booked till 1 o'clock, so I don't think we'll cut you off. For those of you not familiar with this area, just out the door and to the left, if you go down a bit, you'll find washrooms on the left. And I think that's the only housekeeping item for that. For our online guests, for your questions, if you're joining us online, for those on a laptop or a desktop, the chat is on the right side of the screen. Enter your question in the chat, and then when the question and answer time comes up, one of our group will bring that question forward. On other devices, so phones and tablets, if you look just below the screen, the video screen, there should be a live chat area that you can click into, and again, enter the question in that area and we'll bring it forward at the time that we answer questions. Today we gather on Treaty 4 territory, on land that has been occupied for centuries by many First Nations peoples, land which we agreed to share in the treaties but have failed miserably to honor. I am trying, and will continue to try, to learn from the First Nations teachings in a way that can lead to a good relationship and respectful living out of my treaty responsibilities. I am grateful for all that the land gives to support my life and the beauty it provides that nourishes my soul. Though it is bitter winter, I am grateful for the gift of snow, which will provide some moisture for our drought-stricken land that struggles to provide for its plants and its creatures. I am grateful for the gift of cold, which allows the perennial plants of this land to rest and strengthen for the next season of growth. and which will reduce the populations of insects like mosquitoes and Lyme disease carrying ticks. If you are not from Regina, please take a moment now to silently acknowledge the land from which you join us. Now, on to business. I will introduce our three presenters. First, Tom Atkins is a mechanical engineer and retired vice president from Stantec Consulting, having been involved with buildings and sustainability for his entire career. During his 40 years of experience in the consulting engineering industry, he has been involved in mechanical and energy systems design and modeling for a broad spectrum of building types, locally, nationally, and internationally. Matthew Dipple is a co-owner of Airtight Engineering, a Saskatchewan consulting firm specializing in energy modeling and mechanical design for energy-efficient buildings. Matthew has worked in his capacity as an engineer on numerous design projects which utilize heat pumps on the Canadian prairies. Last but not least, Doug. Doug and his wife Suzanne started with grid-tiered solar in 2017 and have migrated to a full residential microgrid. Recently, they've added a heat pump in an effort to reduce their heating carbon footprint, collecting real-time data on power consumption. Doug is an engineer currently working with the U of R in Regina. Let's begin.
So, thank you for joining today. As a few people have noted, it's a pretty appropriate day to talk about heating in Saskatchewan. And for us mechanical engineers, this is known as a design day. So it's just about the right temperature and the wind speed to really put things to the test. So today, Matthew and Doug and I are going to talk about heat pumps, specifically how they apply in the province and in our climate. And I think that it's important that we talk about their use as part of overall decarbonization. And there is a lot of talk in the news. There's all kinds of publications. Most of them, rightfully so, don't really get into the specifics of it because it's a somewhat complicated topic. And depending on how you're going to apply it, there's a lot of different influences on how you're going to go about it. It's I like to equate it to buying a vehicle. You can buy a truck, you can buy a car, you can buy a subcompact, four-wheel drive, gas, electric. Like there's a lot of different options, and so the term heat pump is like an umbrella term. So for the first part, I'm going to do the introductory part of this presentation to give you a bit of the basics, and then Matthew's going to get into more specifics, and finally Doug's going to give us some real-world examples of how they work. So I think I'll get on with giving you a bit of background, and then if we step back a couple of years ago, April 2022, City of Regina adopted the Energy and Sustainability Framework, and it outlined plans for the city's transition to becoming a 100% renewable city by 2050. It was acknowledged at the time that it is a very ambitious goal, and we stated, I spoke to council, pointed out that there's going to be efforts by a huge range of people to get that done. Notably, we've pointed out that most of the energy consumers in the city aren't actually under the city's direct control. So it's more about them being looking after their own house, but being a catalyst towards getting the rest of the community to get on board. So the ultimate success of the framework is going to require the efforts of all of us, and it's clear that there's lots of unanswered questions when you get into the nitty-gritty of application. Some of them are technical in nature, some of them are more like policy in nature, economic and social, and so all of those need to be addressed. There are several groups. We were very happy to hear of Karos picking up this area and asking us to do the presentation. I have been working with the university over the last year and a half or so, putting together a series of seminars and symposiums, not just on heating buildings, but on other aspects of sustainability. And it's going to take the efforts of all of those and many more to get this done. And so what we want to do is we want to make real positive change. It's not about talking about things, it's about kind of getting down to business and doing the hard work, the planning and the execution and financing and communications and all those things that go into with making a big transition. So this is a little slide from the University of Regina, and what our goal was. We had the university's approach is a little bit different in that they were trying to help the city and answer some of the questions or pull out some of the questions from a wider audience as to what are the roadblocks or impediments to making progress. And so the goal was to hear from a large group of stakeholders and to share information and ultimately to get projects underway that would make some efforts towards reaching our goal. So what's already happened? So beyond those little bits of things that we know about, there's real change happening in the wider economy, not just in Saskatchewan. Like significant, you may not realize it, but there's significant efforts to move codes, building codes, forward, and the new editions of the building codes, which are coming into effect, have a much more aggressive approach at energy and not just safety and durability for buildings. So they've had an energy aspect for some years, but they're moving much more aggressively to a stronger position on energy use. So they are tightening up, and they are going to further tighten over time. Now, the problem with codes and standards is that they don't really come into effect unless you're building something new, or if you're doing a major renovation where the permitting authority makes you meet the new code. But that's going to change. There is a discussion in the code world that's going to ultimately may move towards actually having renovation codes as opposed to new building codes. And there's a strong debate in the policy circles as to how you can make that happen, considering that most people, they own their assets, and so it's a very complicated topic. Another part of it is the marketplace is moving. And so often what we see in big transitions for anything is that marketplace moves often are an impetus for the society to make a change. And so you might remember back in the 80s and 90s where we had water scarcity was becoming an issue, and in particular jurisdictions in the U.S. South and Southwest, it was a really big deal. And so there was a move afoot to move to low flush toilets. And so there was some code changes for new construction in the U.S. South and so on. But eventually what happened is the marketplace moved to that's all you could buy. So whether or not it's a code, whether or not you want to or not, at some point in time, the marketplace will move to the fact that most of the products being made available will be in a certain, made a certain way. And we are on the tipping point of seeing that with heat pumps. All the major manufacturers in North America and indeed around the world, they've been making heat pumps for years. I think that you will see in the coming years a move away from straight air conditioners and manufacturing lines, production lines moving to heat pumps. So that's something that we're watching. So beyond incentives and so on, the supply side may influence where the market goes. That's one thing. The electrical grid is a very important aspect of all of this, because in cold climates and in places where hydropower has been less of a resource, the carbon intensity of the electrical grid is an influence on how we create carbon in the rest of the economy. So there's been a tremendous amount of work that SaskPower has done and is doing right now in starting that transition, doing real world work, planning and execution, and there's a host of efforts that they're taking on. And I would, if you want to get more information on that, I strongly encourage you to go to SaskPower's website. You can also go to the U of R's research page for the Faculty of Engineering. There was a presentation that SaskPower made, details a lot of the things that are going on with the electrical grid. Okay, so now before we go any further, it's important to talk about the rest of this electrical supply issues for Saskatchewan. So beyond the carbon intensity of the electrical grid, we want to talk about the state of the entire grid, because not only do you have to produce low carbon power, you have to be able to get it to people. And so a lot of the efforts that SaskPower is going through right now is modeling the electrical grid. And so that's going to be an ongoing and complicated effort. And along with that is many modernization things that have to go along with it. So I'm going to borrow some SaskPower information that was presented, and this gives you an idea of where the power production is as of 2022. This is changing and evolving. SaskPower has projects ongoing all the time. It also depends on what year it is, whether or not water levels are high enough to get the most out of hydropower, but this generally is how the mix of power, and we are going to see that change in the next few years, and that will change what the grid intensity.
Quick question, Tom. Is this slide deck going to be made available publicly?
Yeah, it's all publicly available information. Yeah, yeah.
Is this deck going to be made available?
Yeah.
I can do that for
Yeah,
you.
sure. Unfortunately, a lot of my slides don't have a lot of words on them.
That's good.
That's good.
That's good.
I like people listening to the words, not anyway, so there's probably a more current version of this forecast for emissions, but as you can see, there is a downward trajectory for SaskPower and their emissions, and that is important. So this is total amount of tons of carbon. It's not the grid intensity. So to get what the grid intensity is, it's really a factor of how much power you're producing and how much carbon you're producing. This only talks about the amount of carbon. So we'll get to that intensity in a little bit. So, for 2021, SAS Power reported a grid intensity of 0.583 carbon equivalents per gigawatt hour. And in 2030, that is forecast to drop to 0.2. And now you get that by taking the 2030 target for emissions and using the 2030 amount of power, because the amount of power SAS Power is producing is increasing over time as well. So they're decreasing carbon and increasing the amount of power. So that's leading to a big drop in the grid intensity. And why this is important is that this is the number from which you establish how much an electrical device emits as carbon. And so that's more important than what the gross amount of tons of carbon are. But look at that. That's a 65% reduction in carbon emission intensity in the next number of years. 2030 is just around the corner, really. Okay. So we've talked about the grid intensity, and we've talked about all the work that SAS Power is doing. But it means that there's a humongous amount of transmission and distribution work, and it also leads us to another issue, is that we will never, and SAS Power is not alone in this, all electrical grids have the same problem. If the whole world decided to move to electrification right now, there is no way that any utility could ever provide it at an affordable level. Never. Like, you would need, there are studies out there that say, I forget what the numbers are, 2 to 3 times the price of power if we were to try to build out, if you just did a straight energy swap, take out all the use of fossil fuels and just put in electrical power. It's not going to happen. So one of the things that goes hand in hand with this is trying or needing to go to energy efficiency. So the entire industry will say that along with decarbonization, we also have to meet a move to lower energy consumption. So this is my pitch to tell you that you should be doing things in the right order. And right now, the thing that you can do right now and affect your carbon emissions is reduce the heating load in your house. So you can do that by insulating. You can do that by tightening the building up. You can do that by operational things like running your house a little bit cooler in the winter and warmer in the summer. But there's doing less loads of laundry with hot water and using cold water. Don't use the dryer as much. Like, there's a ton of things that can be done that aren't super technical in nature, and they're available for you to put in place right now. So, and I think it's important to say that for us to do our part, as you know, we're talking about everybody doing their part, the homeowner community needs to move towards energy efficiency. We're seeing that energy efficiency move on the new build side. So the home builders and the codes are driving new homes that way. We need to see the existing building stock made more efficient. So, just a little image of what a leaky house looks like. The other things you can do is integrated smart controls for your system. Like, all of these things in and themselves aren't magic bullets, but they'll reduce your loads by like a few percentage points for each one. And they're fairly low cost items, LED lighting and so on. So that's my pitch for energy efficiency. Now we'll get to heat pumps. First, as today tells, we're in a cold climate. And with the cold climate, that presents technical challenges. And we'll kind of set that aside. The second part of it is that we're in a heating dominant climate. That's to say, in our engineering terms, we require more heat than we require cooling. So, and we always look at energy consumption throughout the whole year. If we were talking about a battery that had something that could charge the battery and use power from the battery, we would be in a system that uses more power out of the battery than puts in. So we're always trying to, the buildings that we have, and particularly residential, small single-family homes or smaller multi-unit homes, we are strongly heating dominant. And so that's something to keep in mind as we go forward. So what is a heat pump? So it's a refrigeration cycle. If you have a fridge in your house, and I know you do, that's a heat pump. So it's moving heat out of the fridge and into the house. So all a heat pump is a refrigeration cycle, and in the vernacular of buildings, specifically, it's one that can reverse itself. So it can act as either putting heat into a body or take heat out of that body. So your home air conditioner is a heat pump without the reversing valve. So it's taking heat out of the house and putting it into the atmosphere. You know, for heating the house, you want to take it out of the atmosphere and put it into your house. So the concept's been around forever. I think I read that it was actually in the 1880s that the original thermodynamic conceptualization of moving heat was taking place. It was commercialized in the mid-1900s. Willis Carrier developed the vapor compression refrigeration cycle, and when they were always talking about cooling for things like food production and safety, high occupancy spaces like movie theaters. People went to movie theaters. Let's make them cool so people can get some respite out of the heat. But at the same time, they're also talking about, you know, moving heat the other direction. So I just want to check my notes here. Okay. I just wanted to point out that these are typically electrically driven, but they're not all electrically driven. Okay, so things to know about heat pumps is how to talk about their energy use. So you'll see terms when people talk about heat pumps. COP is a commonly used term. That's coefficient of performance. That's a measure of the amount of energy in to the amount of energy that it moves. So if it takes 1 kilowatt to drive the compressor, to rotate the compressor, and the COP is 3, that means that it is going to put 3 kilowatts of energy into the house. Housing is what we're talking about here. So it's moving, it's taking 2 kilowatts of heat out of the atmosphere. The 1 kilowatt of heat that it's using for its force ends up as heat in the cycle, and 3 kilowatts comes out. So you're getting a 3 times multiplying factor. So importantly, what you should know is your furnace. If you have a super efficient furnace, it's like in the 95% efficient range, 97% percentage range. Its COP is 0.95 or 0.97. So you're talking about, it's the efficiency. It's a way of talking about efficiency. Okay, let's talk about quickly about the different types. So there are air source heat pumps. On the right, that's one most people will be familiar with. So this is like an air conditioner. A coil outside has air drawn over it. The compressor pumps refrigerant through that coil, pulls the heat out of it, and moves it inside where it goes through an expansion process and through a coil that expels the heat into the airstream of a furnace or of the zone heads and the refrigeration just goes around a circle. That's one way. The second source are water source heat pumps. So that's using either groundwater or some water body of some sort to extract heat from that water body and then put it into another water body or into an airstream. So that's something that we'll get back to. And then there's industrial heat pumps, and they can do all kinds of crazy things, again, with air and water. But so the technology that we're talking about is technology that's very scalable. So this is the same technology that we're going to talk about today, could be used in a single family residence, or it could be used on a campus. Like there, it's totally scalable. So I talked about other sources of energy. So if you go on Sask Energy's website, you might see reference to gas-fired heat pumps. And really there's two forms of gas-fired heat pumps. One that uses natural gas to turn the compressor. And so instead of electricity turning the compressor, the natural gas engine is driving the compressor. And that is the same type of refrigeration cycle. That's still a vapor compression cycle. Then the second method is quite different. It's called absorption. It uses heat as the motive force for heat exchange. It's quite complicated. It uses salt brine and crystallization and pressure change. Again, it's been around forever. It's been around forever really on large pieces of equipment. These were very common in the 50s and the 60s, where you had, say, hospitals. St. Paul's Hospital was a classic example. St. Paul's Hospital in Saskatoon for years had an absorber heat pump. It used excess steam in the summer to drive the absorber chiller. So they're both doable. The important thing to remember with gas-fired refrigeration devices is their COP is lower. They're the ones that I've seen. I don't think I've seen one better than 1.6. So I think 1.4 to 1.6. But there are places where they apply properly. So. What's new and what's changing and evolving. So heat pump technology is always evolving. It's not making step changes really. As I said before, heat pumps have been around forever. They're working on compressor design to make the compressors more efficient. They're working on refrigerants because the type of refrigerant that you use has different properties and they can extract heat more or less efficiency and at different ranges. And so that's a really important factor for us. And then there's packaging applications. So how the heat pumps are packaged and sold into the marketplace. So an important thing that's going on right now and has been going on for probably about 2 years is NRCan with the Department of Energy in the US, really led by the US, has a heat pump challenge on right now for manufacturers. And that challenge is deliberately trying to move the manufacturers towards more efficient heat pumps and heat pumps with a wider operating range. So they notably can operate in colder climates. So they have some very specific goals. It's a very fast project. In fact, I think that Lennox has already commercialized some of the research that they have done. They're moving from a phase now of research where they're going into in situ testing right now. Like that's happening this summer. Just yesterday I got a notification that they've had 4 more manufacturers join. So this stuff is happening quite dynamically in the marketplace, and we are going to see results. So here's an important chart. Now this chart shows the distribution of temperatures, climate temperatures, in aggregate for Canada. So this isn't specifically Saskatchewan's environment. but you can see on the left-hand side are the very cold temperatures, -40, and the right hand is the upper limit of heating requirements, which is considered to be 18 degrees C. And so if this chart were and these are a representation of the percentage of time that we're in these temperatures, that we experience these temperatures. And you can see that there's a whole bunch of the most are around the 0 mark. Now, if this was for Saskatchewan, this chart actually moves to the peak moves towards the left. Not a lot. It's surprising. It's not as much as you think, and but it is to the left. The other thing to consider, however, is that climate modeling suggests that our climate is moving to the right. So I suspect that in 20 or 30 years that ours will look more like this than otherwise. And so that really doesn't change technical requirements. It does change the economics of things because you're going to get more hours that are of moderate temperature. So notably, you should look at the colors on the top. These are the percentage of times of heat demand, and the stripes are in areas for heat pumps, relative to heat pumps. So in the blue zone, heat pumps right now categorically work like excellent, perfect. Their coefficient of performance is in a good range, and so you can see that 80% of the time, right now today, heat pumps actually function great. And if you look to the middle band, that's where we have emerging technologies or some existing high-end technologies that work. So you can buy a heat pump today that works at -25. It's more expensive, and the efforts are to move product development so that all products in an affordable way can operate that. But you can also see that you're getting the vast majority of heat demand will operate on a heat pump without any reserve or backup. The thing to remember out of this slide, though, is that they work, but you do need backup. And so backup, like your heat pump right now, it turns off when the temperature is too low. So what happens then? You instantly have the heat demand on the house. So you need to replace that with either electric resistance heat, which I highly discourage, because you don't have the power supply to your house right now. SaskPower will hate you, and you won't be able to afford it. So I highly discourage you from doing that. There are some places that are very remote that don't have natural gas. That's what they have to do, but that's not the answer now. But your gas furnace, if you have an existing home, your gas furnace is sitting there. It's already installed, and so your gas furnace is going to kick in. So the question becomes, are you saving a lot of carbon? That's for later in the presentation, and you'll get to hear from Matt. But what I likened this to is a hybrid car or a hybrid vehicle. So the electric motors can drive the vehicle for a great deal of operating conditions, and then the gas engine takes over. Same thing here. An electric heat pump can work in a vast range of outdoor operating conditions, and then it goes to the natural gas backup. And so I have not talked about geothermal geoexchange, but I think that Matt's going to talk about that. So I'm going to give it over to Matt right now.
Okay, awesome. Thanks. That's perfect. So I'm going to, if I've already been introduced, get into a little bit more of kind of the homeowner side, like as a, as someone looking into heat pumps for your home. What does that look like? So we're going to talk about a few things. First of all, background on heat pumps with respect to your home, so sort of narrowing in a little bit on this residential scale. Then the meat of what I'll talk about is sort of frequently asked questions. So I've got a few of them listed there. Are we going to save energy costs? Like, is it going to be cheaper to heat my house with a heat pump? Am I going to save carbon emissions? What's the upfront cost look like? Can you retrofit a house with a heat pump? Some of those questions. And then I've got a few random slides that didn't fit into any other section, which will be the additional details. So this picture here is a project that we did the design on. It's up in Cumberland House, I believe, and it's got 3 heat pumps on it, and it has a backup wood pellet furnace, I guess. They don't have access to natural gas where they are, so they went with a heat pump system for their primary heat and then wood pellet furnace for their secondary heat. Okay, so a bit of background. So if you're a homeowner, you might be thinking, well, Tom just talked about how important it is to save energy. So how can we save energy in our homes? Well, these are the main areas where we use energy in the home. So the biggest one that you should notice, should not be a surprise, especially today, is space heating. And so, especially on a typical home that exists right now, or even a new home that's just sort of built to the minimum requirements, space heating is going to be by far the largest energy use. Next one is water heating. So water heating comes up next. It actually takes a lot of energy to heat up water. And after that, we've got our appliances, and then lighting. And see how small space cooling is? We do need to cool, but it's very small compared to how much heating we need in this part of the world.
What is a PJ?
That is a petajoule. So this is a graph for all of Canada. So this Saskatchewan would actually have even more space heating requirement. So this is all of Canada, and so a petajoule is a very, very large amount of energy. Yeah. So usually, to give you a sense of scale, a typical house in Canada uses 100 gigajoules in an entire year for all of this entire circle, all of their energy uses. So 100 gigajoules, the petajoule is 1 million times that. So, so that's a lot. Interestingly, we can actually use heat pumps in different places. If you think about appliances, here's one that you use already, refrigerator, as Tom mentioned. We can use them in space heating, which is sort of where we're focusing today. You can also get heat pump water heaters as well, which we'll touch on a little bit. And space cooling, of course, your air conditioner, it's a heat pump. So we can see that a heat pump is actually a great tool that we can use as homeowners to conserve energy. And sometimes a heat pump is just the only way to do something. So to make a fridge cold, we use a heat pump in our refrigerator. So these are what some of the different heat pumps in your home could look like. So your refrigerator, everyone's familiar with that. Just beside that there is a heat pump water heater. That's one particular style. So it's got a little heat pump built on top of it. And it's actually taking heat from the room surrounding the water heater and putting that heat into the hot water. So it actually cools down the room a little bit. So in the wintertime, your heating system has to work a little bit harder. In the summertime, though, you get some free air conditioning from your heat pump. You can also have styles that look more like the picture on top there, that look more like a heat pump that would be used to heat your home as well. So heat pump water heaters are something similarly that have been popular in other parts of the world, notably Japan, but we're starting to see more and more coming into Canada. We've also got so at the top would be for space heating. So that's a small heat pump for heating a home. And on the bottom, we've got a clothes dryer. So you can get a ventless dryer. Some of you may have done some research or heard about these. There's 2 types. One is a condensing dryer, and the other is a heat pump dryer. So the heat pump is probably a little bit more expensive than even the condensing, but it's the most efficient. So the heat pump version is, what it's doing is it's working like a dehumidifier. So if you have just a portable dehumidifier, that is actually a heat pump also. But your ventless dryer that uses a heat pump is essentially just a dehumidifier that's dehumidifying your clothes instead of the space. So you get to dry your clothes at a lower temperature, and it's much more energy efficient. As well, if you think of your standard electric dryer or even gas dryer, you've got a vent, a pipe going outside, and then you're blowing all this nice hot air straight outside. And so you've paid to heat that air up, and then you're just chucking it outside. So the ventless or heat pump dryer is a great option too. So Tom's already talked about some of the excitement about heat pumps, but just to really push that home, what's exciting about a heat pump? First of all, just look at the efficiency, right? So the efficiency, we can break that 100% barrier, because instead of just burning something to generate heat, we're actually moving heat. So we're taking heat that already exists in one place, we're kind of crunching it down and compressing it, and then moving it to another place. And so an air source heat pump, maybe over the entire heating season, maybe it's about 200% efficient in our climate, roughly. A ground source heat pump, so that's geothermal. Some people would call it geothermal. More correctly, it would be called geo-exchange. It can get, in our climate, maybe close to 300% efficient. And in warmer climates, maybe it's more like 350, 400% efficient. So that's pretty amazing, considering the best we can do when we're burning something is 100%. Here's looking at those water heaters. So we're looking at this UEF for efficiency, which you can think of those, just move the decimal place to the right a couple and think of that as percent efficient, right? So 0.57 would be 57% efficient. And so same thing, you can see our different types of water heater. We've got sort of a typical natural gas tank water heater, tankless, electric tankless. We're kind of moving up in efficiency, but we're topping out at 1 until you move to a heat pump, and then you can get over 1, right? So we've got the hybrid heat pump. That's the one that we saw the picture of. So that's the one where it's just taking heat from the space around it, versus the CO2 water heating heat pump. I only know of one on the market in North America at the moment, but there's certainly more that are starting to enter the market. That's the one where it's taking heat from outside, similar to a space heating heat pump. So just to note, with a hybrid heat pump, the one that's just taking heat from around it, in the winter time, its efficiency is reduced to the same efficiency as your building heating system. Because if you think about it, you're stealing heat from the building, then you have to replace that. So if you've got, say, an 80% efficient, really old furnace or boiler, then your heat pump's only really 80% efficient, because that's got to replace the heat that it's taking. In the summer, on the other hand, you're getting free air conditioning. So just interesting note with that hybrid heat pump. So really they pair best if you're using a heat pump to heat your building, then it pairs well with using a heat pump water heater to heat your water as well. And then just talking about dryers, I like this. So the graph on the right, this is from Sask Power. They've got a nice little tool where you can see how much energy different appliances might use in your home. So this is a standard 4-person house, and we can see your clothes dryer is up at number 3, right below air conditioning and stove. And so if we're looking at appliances that we can make more efficient, the clothes dryer is right up there. If you move from a standard electric with a vent out the wall to a heat pump dryer, you are roughly cutting your energy use in half on that dryer. If you want an even cheaper option, if you move to a clothesline, you're cutting it by 100%. So there we go. So what's exciting about heat pumps? Efficiency. That's the first thing, right? So we're breaking that 100% barrier. We're getting to really efficiently move heat instead of generate heat. Versatility. You can see how many different applications they have in our homes. And as Tom mentioned, they also scale up to commercial, to industrial scales as well. And we do have opportunities for electrification. So as Tom mentioned, in our climate, it's not like we want to necessarily electrify all of our peak load just because of the impact on the grid, but we want to electrify when it is most efficient for us to do so. Heat pumps get us there. So for the remainder, I've talked about a few different types of heat pump. For the remainder of my section, I'm just going to talk about heating and cooling. So we'll forget about all of those other types of heat pumps, but just know that they exist and there are other tools that you can use as well. So I like this picture. This is a particular manufacturer, but a heat pump versus an air conditioner, go figure, they look exactly the same. One has another valve in it that you can't see, a three-way valve, but it's funny, sometimes in the media it's like, oh, heat pumps are scary, and not to pick on the media, but to say, I guess, yeah, you guys are here, yeah. But like in popular parlance, we think heat pumps are scary and unknown and new, and they actually, when you see one, you might not even know that you've seen one, because sometimes they kind of look like the thing that we're already used to. So I think that's interesting.
Just to interject.
Yeah.
I mean, I was in university in the 1970s, and we were doing heat pumps then. Mm-hmm. So and they were commercially available. So it's nothing about it is new. The only thing that's new is that they're better than they used to be.
Yes. Yeah. Yeah. That is a great way of putting it. Yeah, for sure. Okay, so I think we've talked about this enough, but basically an air conditioner is just a type of heat pump that only works in one direction. So we already talked about this a little bit, but just to reiterate, we can talk about heat pumps both in terms of the source of heat and then also the way that they distribute heat. So on the right, I've got two pictures. The top is an air source heat pump, so it's taking heat out of the air or cool in the summertime. And then the bottom is a ground source. So you've got some sort of underground loop. It's running water or water mixed with glycol in that loop of pipe to take heat out of the ground in the wintertime. And then it could run in reverse in the summer to put heat into the ground and cool your space as well. And so I've broken out ground and water source, but really they both have a pipe in the ground or a pipe in an aquifer. So we could sort of group those together as well. In terms of distribution, we've got a few different types. So they actually work with all types of heat distribution that you would see in your house already. So if you've got a furnace with forced air distribution, they work with that. If you've got a hydronic system with radiators or maybe baseboards, they can work with that as well. And then there's also an option for ductless, which you may have seen in people's homes already. In the past, these were just air conditioners, but now more and more they're moving towards heat pumps. So that's sometimes they're called a mini split. So the picture on the left there is a picture of a ductless mini split. So it's got the little heat pump outside, and then on the inside it's just got this kind of cassette mounted up high on the wall, and that's what's providing your heating and cooling. And just a note about those, air is blowing through them, but it's all just air circulating from inside. There's no air that's coming from outside. There's just two pipes that are moving refrigerant from outside. Okay, so let's talk about some questions. So the question, do they work in Saskatchewan? Yes, they do. I just put up three pictures of different projects that we've worked on that use heat pumps to heat in Saskatchewan. So the top one there, the Cumberland House Cree Nation, that was the three heat pumps you saw a couple slides ago. And the bottom left is a housing co-op in Saskatoon. It's a super efficient building. It's probably one of the most efficient buildings in the province. And they heat with a heat pump, and they have backup electric resistance. Then on the right, that was actually a greenhouse project. So it's up in Montreal Lake, and they probably have a month or two in the winter where they don't plant things. So I don't know if they have any backup, but that heat pump, it's a Mitsubishi cold climate. It can run down to minus 30. So lots of heat pumps will be rated to minus 25, and some are minus 30 as well at the moment. So for the sort of the cold climate lines. And then my bottom point there was the one that Tom was talking about, the competition that the U.S. Department of Energy is having right now. Okay, so this question, will a heat pump save money and emissions in Saskatchewan? So I did a little ciphering on this. I used a tool that Enercan puts out called the Air Source Heat Pump Sizing and Selection Tool. So right now we're just looking at air source heat pumps. We aren't looking at ground source, just looking at the air. And I actually, seeing Tom's slide with SaskPower's projected carbon intensity, I actually used a higher projected carbon intensity for 2030. So we'll talk about that in a couple slides. But I decided to look at three houses. So the one on the left is not very efficient. It's a pre-1980s, it's a typical house, and it's got a typical house heating load. The middle one is like a modern, efficient house. So it's new. It's nothing crazy, but it's just like, you know, standard best practice. So it's going to be better than code minimum, but not, you know, you aren't creating some fancy earth ship with like, you know, windmills on the top or anything. And then the one on the right, this is like best in class. So it's not passive house certified, but if you're familiar with the passive house, it's using a lot of passive design techniques to really drive down your energy use as much as possible before putting in the heating system. So we've got 3 houses, and we're going to look at 3 different combinations. So one is natural gas heat. This is our base case, right? No heat pump, just natural gas heat. This is what we're comparing to. And then we're going to compare 2 alternatives. One is a heat pump with natural gas backup, and the second is a heat pump with electric backup, which, as we mentioned, sometimes looks better, but is also hard on the grid in terms of that design day when it's minus 30 out. Okay, so here's our scenario 2. So we've got our little heat pump there and still natural gas backup, and then our scenario 3, our little heat pump with electric backup. So in terms of cost, recognize this is a preliminary calculation. I did not do a lot to optimize these situations, so you could certainly do more to optimize. I just picked a random manufacturer that I'm familiar with their product and know that it works decently well and is pretty accessible in our market. But this is what I found for cost. So 2024, right now we have no carbon tax on our heating as of January 1st, which let's not talk about any further. But even with no carbon tax at the moment, our 2 scenarios in the 1980s house and the sort of fairly efficient new house, we're spending more money. So you might be surprised. People are saying, oh, heat pumps are so efficient, I'm going to save money, this is going to be great. Well, the thing is, natural gas is 6 times cheaper than electricity at the moment. And so even though your heat pump is 2 or 3 times more efficient than your natural gas furnace, that 6 times is hard to beat. So you're actually not saving money if you're heating with a heat pump. There are caveats to that, right? If you're just running your heat pump right at its peak efficiency, even then you're still not saving money. But it's getting close. So in all of my scenarios, we're not saving money except for the very right-hand side right now. So this is our super efficient house. It's saving money if it's got electric backup, and that's assuming you don't have a gas service. So you pay $26 a month just to have your gas service hooked up. So that's $330, $340 a year. And that $340, that's what's making the difference between that last case saving money. So if you take out your gas service altogether, you get to save that hookup fee, and that's what's putting you into the green there. Note that with the most efficient house, it is challenging for the grid to heat that house on the coldest day, but it's way less challenging than it is for the grid to heat our 1980s house, because this house far to the right has a much smaller heating load. It has a very small heating load. It's like 3 times smaller than our other house, and so that's something to note as well.
Sorry, can you clarify what the arrows are?
Yeah, so the up arrows, the red ones, red is bad and scary. It means our cost is going up when we're using a heat pump.
So there's 2 arrows on
Yeah, sorry, 2. Okay, yeah, good question. So this is our heat pump with natural gas backup, and this is our heat pump with electric backup.
And that's
a good question.
estimated cost.
Estimated cost per year. Yeah.
It's going up.
Yeah, exactly. So if I had my 1980s house and I'm supposed to be by the mic. If I had my 1980s house and I had a heat pump, an air source heat pump with natural gas backup, maybe I'd be spending an extra $550 a year on heating versus if I just had natural gas. And if I had a heat pump with electric backup, maybe I'd be spending $500 extra a year versus just natural gas. Does that make sense? We're comparing a lot of things on this slide. So the main points that I want to get across though are, so look 2030, see how much things have changed, and that's because I'm assuming the federal government's projected carbon tax of $170 a ton. So when we add that in, we can see how much closer, like we're getting close to even on all of these in terms of cost for heating with a heat pump versus cost for heating with just natural gas. And so, yes, my arrows are pointing up on a lot of those scenarios still, but it's like, this is certainly within the error band of my crude crude calculus here, right? So you might say, hey, I'm spending $87 more a month. That's okay. I don't really care. Or $87 more a year, rather. That's okay. I'm okay with that. Or even 170.
So do those figures allow for increased cost of natural gas? Like, is there any?
I have not factored in increased cost of natural gas or of electricity. This is just the only change that I've done for cost is the carbon tax on both the grid, so the electric grid, and the gas grid. So yeah, I haven't. I mean, yeah, like there's so many unknowns going to 2030, right?
Yeah, in our industry for years, in this province, we have typically said that power and gas prices over the long run roughly balance themselves. They go up at the same rate. It goes back and forth, but if you take long-term averages, for financial predictions, it's within the error. Like there's more, there's many more factors that would put more error into it.
Matt, could you briefly repeat that for the people online?
Sure, yeah. Okay, so Tom was just saying that typically the assumption is that as gas prices increase, electricity prices are also increasing similarly, and so the impacts that's going to have on our calculus between gas versus electricity in this scenario is not the driving source of error. There's many other things that would be more impactful than that. So one of the big takeaways that I want to point out on this slide is just how much of a difference, like we're talking about heat pumps, but it bears repeating how much of a difference efficiency makes, right? Look how big of a difference that is. If you have an efficient house, you're actually not that impacted by carbon tax in 2030 versus no carbon tax today. So when we talk about, carbon tax, it's scary, just make your house more efficient, and that's not a big deal. So that's, I think, an interesting takeaway. And you'll see on the next slide where we talk about carbon emissions, we see something similar. So the green arrows on the bottom, those are representing our carbon emissions dropping when we're using a heat pump versus natural gas. And the red arrows on the top line are our carbon emissions increasing when we're using a heat pump versus natural gas. So my green arrows on the bottom should actually be even more negative because I was using a more conservative, like a higher value for the carbon intensity of our electricity grid. So this is really interesting. We're at this inflection point, right? Where it's at some point between now and 2030, we're hitting that point where a heat pump is emitting more carbon than natural gas because our grid has so much fossil fuel on it still. We're a couple of coal-powered plants going offline away from moving into the green territory. So that's something that I think is really exciting, and it shows all the progress that we've made in our power generation as well.
Yeah, some other calculations I did shows that tipping point is about 3 years out from a planning perspective.
Yeah, for sure.
Again on that, please, for Mike.
Sure, yeah. So Tom was saying that from some study that he did, he's seen 3 years out is that's our point for our tipping point. So that's super exciting. So a few key takeaways. Building efficiency still makes a huge difference, right? So heat pumps are important. They're a great tool that we can and should be using, but let's not forget efficiency. That's going to be our kind of first key step. Carbon and cost, they're both reaching an inflection point. So we're kind of hovering around that point where heat pumps are really making sense. And the other thing is we need to think about the lifetime of our system. So we don't want to just say, I'm just going to forget about heat pumps until 3 years from now. Because if I put in a new piece of equipment today that is going to last for 15 years, 20 years, 25 years, I should be looking over the life of that piece of equipment. Now, if you just happen to have put in a brand new gas furnace or a new high efficiency boiler today, it's not the end of the world, because you can still pair that with a heat pump as your backup heat, right? You can use that heat pump when it's most efficient and then transition to using that natural gas when it's your design day, like today. And I also just want to note there are many other factors that I didn't include in this that are going to impact things, right? So I didn't optimize as much as I could have between natural gas and heat pump energy on those last slides. I just picked a number and went with it. And it's also going to change if you're in an area that doesn't have natural gas available. If you're burning heating oil, heat pump makes sense to do all of your heating load if you can. Solar energy, let's say you've got some solar too, so that's offsetting some of your power consumption. I didn't account for that too, so that's going to impact things. And then geothermal. So everything that we say about an air source heat pump is going to be even more true with geothermal, because it's a third more efficient than an air source heat pump. So it's already hit its inflection point, probably this year, maybe next year.
Plus it works in any temperature, because the ground
Yes.
temperature doesn't change.
Yeah,
So you actually don't need a secondary source of heat.
yeah, for sure. Challenge if you're in the city
Repeat
is
that.
sure, yeah. So a ground source heat pump as well, because it's taking energy from the ground, which is always a similar temperature. It's very stable. Even if it's minus 30 outside, that ground source heat pump can still pump just as much heat as it could if it's 10 degrees outside, because it's not impacted by that outdoor temperature. The challenge if you're in a city is, where do you put your ground loop, right? So in your backyard, in your flower bed, are you going to have a drilling truck drilling in your flower bed? What's the city going to say? What are the underground utilities going to say? So it gets challenging when we have congested infrastructure to put in those ground loops. And they're much more expensive as well. Okay, getting close to the end here. So how much does a heat pump cost? The answer is it depends. Lots of factors. Ground source is more expensive, as I just mentioned. Just a few really rough, like, you should not use this as, oh, great, I can afford one, or, oh, no, I can't afford one. But just think of this as like order of magnitude to just sort of tune yourself a little bit. So the unit itself, you can buy online a cheap mini split for $1,000. It's going to be small. Will it work amazingly in our climate? Who knows? But that's sort of lower end, $1,000. And they can range up to $8,000 for a 5-ton. A 5-ton unit's pretty big. And so that's sort of like, that would be the biggest residential size of equipment you would see, would be a 5-ton. So that's a very big unit. The city of Saskatoon has been doing this home energy loan program, and they've got some unpublished data from that, but they've seen that in 2022, the average installed cost of a heat pump with their program was $10,000, and that had dropped to $6,500 in 2023, and they think a large part of that was actually familiarity for contractors. So first year of the program, lots of contractors were struggling with, how do we price this? There's a lot of unknowns, there's risk. And then the second year, you've got some contractors who are emerging who are like, oh yeah, we can do this. We know how, we don't need to price in as much risk. So that's something that's interesting there. Just a note that cold climate versions, there's usually a bit of a price premium for the cold climate version, just because it's got a bit more kind of system that it's using. And those mini split, the ductless unit that I showed, are usually cheaper than a centralized system. A question, can I retrofit with a heat pump? Do I have to build a new house? Can I retrofit? The answer is yes, you can retrofit using a heat pump. So a great way to do that is to, if you're looking to replace your air conditioner, replace it with a heat pump, get the controls in place so that you can choose to heat with it or just to cool with it for now. And then in 2 or 3 years, when we hit that inflection point, you can fire it up for heating as well. So that's a great option. A couple of questions and considerations. Again, if we can, we want to improve the building envelopes, the shell of the building first, because then we get to buy a smaller heat pump, right? If you have a very inefficient building, you need a bigger heat pump to heat or cool it. But if you work on efficiency first, you get to drive down the size of that equipment. You will also want to ask if you have a furnace or hydronic heat, because that's just going to change the type of heat pump that you have. So if you already have ducts and you're using air to move temperature, then you'll get one type. And if you are using a hydronic system with radiators, you'll use a water-based heat pump. And asking the question, do you want to keep your natural gas backup? So often that makes sense, but that's up to you as well, kind of making that decision. Am I using my gas furnace as backup, or am I trying to just use electric resistance, which we sort of talked about some of the challenges from a community level with that. So seeing the time, I want to make sure that I don't take all of the time. So I think I will see if I have anything else. Maybe the last thing, I think we talked about natural gas heat pumps enough. So we'll make these slides available. I've got there's a few more just additional details, but really the meat of what I wanted to address was in those kind of frequently asked questions. So.
So I'll ask, I got 2 questions, Matt.
Can we save questions till the end?
Oh,
Okay, we'll save it again.
okay, sure.
Don't forget.
We coming in? There we go. Hi. Thanks for sticking to the end. I appreciate everyone's enthusiasm. My name is Doug. My wife Suzanne and I was mentioned in the introduction. Kind of have some first-person experience. I know there may be people in the crowd that have first-person experience as well. But we want to talk about some of what we've gone through in our journey looking at some of these technologies. So again, we have a mid-90s, 1,800 square foot house in the city. And over time, we've done various upgrades. When the house was built with a contractor special mid-range efficiency furnace, and in 2010, we put in a new furnace, and we were kind of excited. You know, we bought a high efficiency modulating gas valve, so 96% efficient furnace. Yep, the contractor was going to give us a thermostat that worked with that valve. They didn't, so we were busy. You know, the house was warm, but we were doing other things. We didn't notice that. You know, I guess we weren't getting some of the efficiency we expected, but that was fine. Then. Really, my background is electronics and electrical, so we really focused on we're going to focus on electrical generation. Like we're going to net meter with SAS Power. We did it in a series of phases of a first set of panels, then a second set of panels that were going to be battery tied, and they were also going to be easily to clean snow off of. So we would kind of have backup power, which then turned into where we fit in this category of what's called a microgrid now, where we can run in various different modes. So we did all that, and you know, it's a funny situation because you're sitting there and we're basically not really drawing power from the grid. We've also minimized our consumption. We had some high usage elements and we got rid of them. And we're not really impacting on our electrical bill, but then we get a gas bill, and we're seeing that we're still using a lot of natural gas, and also we took a trip this summer across to Newfoundland. We drove out to Newfoundland, and sometimes things will strike you that you see that yes, there is a change in the climate. We were in places that we packed very warm clothes and found we were sweating because it was extremely warm in places we didn't expect it to be. So we were aware that there is a social value in reducing our carbon. So the question was, well, could we do anything about CO2? So we're still, we have a reasonably good house in terms of being tight. Windows had been upgraded. we also had an issue on the transportation side or vehicle side, but so then the question was, well, could we shift from fossil fuel consumption to electrical? And kind of knew at the start of this process that it would not, without factoring in the fact that we had solar, we couldn't make the case that, it's going to be cheaper to use a heat pump. We were kind of aware of that. Matt used the number, I think, 6 to 1 for natural gas. I was used to using the number 5 to 1, but I knew, okay, there's this 5 to 1 ratio. But the question was, well, would it work? So I sat down. Sadly, it wasn't with my trusty slide rule, but with a calculating device and said, okay, first off, I had never looked at a gas bill. I mean, you look at you owe this amount, but so then I get into realizing that actually natural gas as a commodity was a little more complex than electricity, because you have the commodity cost, you have the transportation cost, then you have you have the carbon tax. And the first thing that hit me was the carbon tax was essentially the same value as the commodity cost. And I remember a time when natural gas was much more expensive than it is now. Like it's a commodity that can vary. I know we're using more natural gas for electricity generation in Saskatchewan, as is Alberta. We import natural gas from the west. So my sense is just I'm not a gambler, but that these prices are not going to go down. They're going to go up. For sure, the carbon tax is incremental. So then I made sort of the leap. I said, well, if a heat pump's coefficient of performance, its efficiency is 2. I use that as just a ballpark number. I know it can be higher. I know it can be less. And our furnace was 96% efficient. Then what I had was, okay, the heat pump is basically costing us 2 times per unit of heating, 2 times the cost of the heat of gas. So it wasn't cost effective. It would cost you twice as much, but we have a source of electrical energy that we can basically use our credit that we bank with the utility, and even go to the point where we pay the utility, and that's okay because it's at a saving in terms of carbon, and we would feel good about that. So those were our initial numbers. So then the next thing as a homeowner, in the consulting world, they'll talk about informed clients and non-informed clients. And then there's a third category, which are they know enough to be dangerous clients. and that was sort of us in a way, because, okay, we know some things, but probably not the right things. So initially, I was pretty set on the way I wanted our system to work was to go with the mini split solution, because it's cheaper, as Matt mentioned. It also is a really simple control scenario, because you basically set the heating of your backup system at a lower temperature than your heat pump. So when the heat pump can't keep up, you switch over to your backup. It's just really simple. And it also, from a reliability standpoint, you have a completely independent system. But we couldn't resolve the issue of it. I mean, the thing is, you end up with a head unit of some form. So these are just some pictures of a couple of systems where I work. The middle slide there is actually a heat pump that's heating an external office, and then there is a nice solution which you can get, which I actually really like if there's major renos, which is a ceiling cartridge. So it's not extending anywhere, but you've got to have an open ceiling to put it in. Again, uninformed or know enough to be dangerous clients. So Tom and Matt may correct me on some of this, but we couldn't find a place to put it. And we also looked with our contractor. We said, gee, could we take that head unit and could we graft it into our existing ductwork? And he said, I can't guarantee that it will work, and I don't want to do something that you're not going to be happy with. So that was good. The reason also for the mini split, and it comes up later, is ducting losses. And I'm going to make some statements. Hopefully I'll get corrected on if I'm wrong, but they're going to come up. So then we had to then go through a couple of iterations. We had have a Lennox furnace, and for a number of reasons it made sense to go with a Lennox heat pump. We wanted one that was Greener Homes compatible. The one we wanted was not available, and that's kind of a tick box, out of stock, North America, backlog, and this is in 2023. So it goes to, I think, some of the things that have been mentioned before, that you have to think ahead on this a little bit, because North America wide, or even perhaps even globally, there's a lot of market forces that you have to plan for. So we ended up with our second choice. It's the Miss Congeniality heat pump, the XP20, and then we had the other thing that happens that I didn't realize. You have to change out the coil inside your furnace unit because there's some differences in the physics of the fluid, and we needed to finally address the control. So it looks like a thermostat, but it's actually a pretty sophisticated and I'm impressed with control system, because there's a lot of things happening in terms of managing our system. But it is big, and that controller was expensive that we had to add. The other thing we did, since we're doing all this work in terms of impacting our carbon, is we found that we're probably, because it tends to be a lot of times just two of us in the house and we have a big tanked water heater, that we're probably on the pinning the needle as far as inefficiency in a tanked water heater. So we went with tankless, and it's been generally a positive thing going with that way. So before I show some graphs that I'm really proud of, maybe just talk about how this works. So the first thing is the heat. We've had an unusual year. If you think about, we had a little bit of cold weather in November. We had a December unlike any other in terms of warm. So the heat pump, it was just, we're not 100%, but a lot of the load was picked up by the heat pump. And we still did have some call for gas, and I'll mention where that comes in. And it's taken a while, just at a first iteration, to tune the system. So there's a lot more options in our particular case. It's not an on-off scenario. There is decisions you have to make on what you want to happen when, and when you want to be comfortable. And we want to be efficient, we want to be environmentally responsible, but we want to be comfortable. So we're also, and I think that's a viewpoint we also have to realize. The majority of people would probably say, yes, we want to do the right thing, but we don't want to be inconvenienced. So, I mean, the first thing, we saw a very dramatic drop in our gas bill from October to November, but again, the weather was different, a lot of other factors, so there's a lot of things to consider. So, one of the things that we have an advantage in is we get a lot of data off our system. So this first one, if I'll just kind of enlarge it there, this is what the thermostat logs. So it actually logs this back to Texas and then gives us access. So we can get a lot of information on, and it's a bit convoluted, and I've actually tried to get an answer on this, but it logs the time the heat pump is running, the hours it's running. It logs at what load, because the compressor has variable stages that it runs at. It's not on off like a lot of, most of the air conditioners I think that you'll find in Saskatchewan are single stage, and this is a multi-stage or variable stage unit. And now we have that aspect of our gas furnace working as well. So the gas may come on, but the gas may be running at a very low throttle. So we get a lot of information. Though being in Texas and not being used to Celsius, they don't plot below zero. So I don't have that graph. It's just something that who knew it could go below zero on a graph. The other thing we do is we also have because of our solar, we have a system that gives us real-time monitoring on the power that we use in our house. So we whatever circuits we so deem, we log them, and it so happens we used to log how much energy we used on the air conditioner. Well, that now became the heat pump. So we have all that data. Now, I was warned that this was really hard to read. So but essentially, when I was getting ready for this talk, I thought, well, this is what the people in the audience want to see. Maybe in a different form, but we have our high temperatures, our low temperatures, our average temperature, and then one here which was a lesson to me, I think, and again, Tom and Matt could clarify this, but it's not just temperature, it's also humidity that affects how a heat pump operates, because if it's the high humidity, there's more heat potentially harvestable. But there is a new thing as well that you have to deal with, is that your heat pump has to defrost itself. And we often find our system in a defrost cycle. And so you get more heat, but more defrost. It appears to us. So nonetheless, as we go across here, and I'll just, it's more meaningful on the next few graphs, but we get an idea of how many hours did the heat pump run, how much was the gas. And it's pretty much what you would expect, that the heat pump works harder when it's colder. There is gas that is drawn as well. And largely where that comes into play is that, you know, if you have a setback temperature at night, and then you have to, say, jump 3 degrees Celsius when the furnace comes on, the heat pump takes a long time, at least, to make that change. So there is at some point where the controller is saying, you're not getting hot fast enough. You know, it could be that you have doors open, whatever, or it's just simply that you're in Saskatchewan. And so it says, we're going to use the gas to get you close very quickly. But what we do have...
If I can jump in there.
Sure.
Generally speaking, in residential with heat pumps, it's not recommended to use setbacks at night.
Now you tell me?
Just from a comfort point of view.
Yeah.
Repeat what he said, please, to the mic.
It's okay,
Oh,
actually. They're
Tom-
telling me they can hear it online.
Okay, sorry, Tom's question was,
Just-
or statement was,
Yeah.
with heat pumps in Saskatchewan, or heat pumps in residential, it's recommended actually not to have a setback.
Yeah, it's because a gas furnace or a gas boiler has a lot of capacity and it's instant. And a heat pump doesn't have that same huge amount of capacity and a big pick for picking up the temperature quickly. So,
Were people online able to hear Tom's comment?
One person told me that they are hearing Tom's.
Okay. Thank you. What I did add in as well then, and I think I have made a slight error in the calculation. I basically took, assuming you have no self-generation, no solar, I said based on 2024 power rates, what is the cost of that electricity? Now, if you've actually factor in, you look on your power bill, I think it's 14.783 cents per kilowatt hour, but then you have GST, you have the carbon tax, and you have a municipal surcharge. And again, that 10% municipal surcharge, depending how many times they compound, it's somewhere between just over 18 cents to 18.6 cents a kilowatt hour. So you end up the real cost of that energy, or the total amount out of your pocket. So going across from the 29th of December, I mean, I have data back, but this is as representative as it could be. Going across, you can see that on a day like the 29th, where the high temperature was above 0 Celsius, which was nice, and the low temperature wasn't that low. It was not quite minus 11 Celsius. It was under $2. Now, I don't know what estimates are for natural gas heating, but it struck me that, again, you would not be happy if you were simply saying, I'm going to heat with a heat pump, and not realizing that your cost for heating would go up.
Is this the heat pump cost? Just the heat pump?
Just the heat pump cost. Yeah, just the heat pump. So then there's the rest of the house. But I found it was interesting. Like it seemed like a reasonable number, and within the scope of how things may be changing. I also just put it, since I thought by this stage everyone would say no more graphs, Doug. I put it in a table. So here are no more tables, Doug. No. Here are the cost versus temperatures. So again, it's kind of what you would expect, I think. Again, the interesting thing, and I didn't mention it when I had the picture of the external unit, is the chunk of ice under it from the defrost cycles. Like, I actually had to go out with ice melter because that's a pathway to our backyard. There are variables that come into play, such as these defrost, and then there is a heater in the compressor to maintain it at a certain temperature. So there are some complexities. I'm fine with it, but we just need to know. Again, the electrical load. I thought I said no more graphs, Doug, but okay. This one's a little easier, I guess, just comparing 2 days, the 29th and the 30th of December, where the 29th was less load on the heat pump. And I believe this is true of all supported under greener homes, that they have to be variable compressor systems, I believe. So one thing that it's actually quite nice is that the compressor is adjusting its electrical draw according to what's required for heat. So you can see on this curve below, which is only the heat pump, the graph, the first major horizontal line on this graph is 1 kilowatt, and then 2 kilowatts at the top. So it's running in between 1 and 2 kilowatts. When we first fired the system up, in October, November, and it's running, and I was looking at some of the data, a lot of that was in around that 800 watt range, and I'm thinking 800 watts to heat an 1,800 square foot house. That's a single electrical heater you buy at Home Depot set on low on its halfway point. I was kind of bowled over with and again, it was the idea that in that range where Tom on his graph had, where we spend most of our time in around the -4 +4 degree range, our coefficient of performance, I think, is much better than you would. It's not the 2 I used; it might be a 3 or 3.5. So it's a good idea. It's just we got to understand the realities of what's coming along. Again, this is just an expanded view of just what that energy consumption is. And I also just wanted to show, just to sort of reiterate, that during this time as well, like, we did have input from solar. If you get into solar, I mean, there's two things you notice. The one most people think about is, what about all the snow on the panels? And yes, there is snow. You can clear it. Nature will clear it. More importantly, is the sun just isn't up as much when we're around the winter solstice. But we do get some production, which helps offset. How we control? I mean, obviously, you set a temperature. What temperature do you want in your home? When the system acted up when we first put it in, and the first thing the Lennox people in Texas said, "Have you turned off the perfect temperature setting?" Says it never works. So that top setting, he says, it does something, tries to take into account the humidity. So he said, never try and run your system with that turned on. But what's really important for us is we set a range in our controller. We have the range set by this balance point. So because it's integrated with our gas furnace, above 0 degrees Celsius, the gas cannot come on. Below 16 degrees Celsius, currently where we have it set, the heat pump doesn't run. And in that mid-range, the system is picking, again, either what we need for a response rate for temperature changes, or it will always defer to the heat pump first. Why is it set at that? Because one thing that this particular vendor is very secretive about is what is their actual coefficients of performance versus temperature. I've actually written to see if I can get them, but there's, when you're at a point where you're below, if you're at 1.5 or 1.3 for a coefficient of performance, it just doesn't seem to make sense to me to be essentially working the compressor that much. Like, if we have the gas, we know at some point we're going to need it. But that's how our system is controlled. So, and so Suzanne and I talked about this because I wanted to, to know that this was valid. But what we're finding qualitatively, actually, the house seems more comfortable with the heat pump. I think part of that is because it is tracking our temperature, or our it's not an on-off situation. It's running for a long period of time at a low load. Again, then we found this issue that you had to start asking for heat much earlier on the heat pump because of the setback. And we do set the temperature back for comfort as well. We like to sleep when it's a little cooler. And the gas is whenever there's a change, the gas kicks on, and there's lots to tune up on the system. Some things we learned, and this one, after I'd found this out, I did find this on Enercan's website, I think. They phrase it a different way. But the heat off the coil when we're running in the heat pump mode is not high. It's about 29 degrees Celsius, which again can warm the house up. But it's written in Sharpie on our ductwork that the furnace temperature is 62 degrees C when it's running flat out. And so then I took my trusty thermometer, the thermocouple, and I measure there, and I ran up while the system is still running, and I measure what's coming out of our ducts, and it can be between 2 and 3 degrees less. So I looked at that and said, we should insulate our ductwork in the basement. I actually looked on the National Building Code because I was curious. We're a mid-1990s home, and I wondered, well, did they call for that in homes now? Because they do in the States in some areas. And I couldn't still find reference. They reference another group called the Society of Heating and Refrigeration Engineers, ASHRAE. They say follow their rules. But I'm looking at this saying, why don't we insulate basement ducts? And so off to Amazon and got a bunch of insulation, and haven't put it up yet. We have to actually seal some of our ductwork, but I will. But to me, it seems that there's a lot of value in the heat coming off a heat pump. That's a strange way to say it, but that 29 degrees, because it's harvested, or it's energy that's moved, and it's of more value to us to try and heat the house, we don't want to lose it in the ductwork. It's part of this tightening up the house, and then tightening up our envelope. One thing that when we go through the energy audit, they did find 2 leaks in the house. We had a degraded seal on our attic hatch, so that was pretty easy to fix. And then we had a back door we had to shim, and then they identify we lose, I think, 13% of our heat through our windows. And I'm actually kind of wondering why it isn't more accessible to get storm windows, interior storms. They used to make them here in town, actually, with plastic. I actually phoned the plastic dealer, Davy Plastics, got a price of $8 per square foot. They say they sell them to people. They put them on with Velcro. And so, to me, that is real low-hanging fruit to actually address windows. But that again, that's an opinion from a client who knows enough to be dangerous. So again, one of the things that we discovered, and it's echoing something that was said, is there's a learning curve for homeowners. I think sessions like this are great, the fact that people are coming out to them. The other group that's still coming up to speed is the contractor community. There are models in the heating and ventilation residential, at least that I've seen. There are some that are trying to say, give us, basically so much a month that everything's taken care of, but you have one flavor of technology. There's some people that are, trying to be very cost effective. And then there are people that are trying to get into different technologies, but they don't know if the market's there yet, and they have maybe one or two people of their technicians that know this. There was one person for the contractor we were working with that knew heat pumps better than anyone else, and at one point he had to leave our system because there was a heat pump down at Katepwa Lake that he had to go deal with and then come back. He was very polite about it, but it isn't as known, and knowing how to answer the questions isn't as well known as I think we would have. And then the other thing that I guess it struck me within the context of this discussion is that that there are programs like there's a subsidization through the Greener Homes program. There's a subsidization for the water heater through Sask Energy. But if you look at these programs, they're not accessible to everyone. Like, you've got to pay up front for these programs, and I somewhat wonder about that. If we're really making this accessible. So again, heat pumps, they can save energy, but I don't think they save money unless you have alternate generation. So that's just echoing what's been said. And just one quick comment though on that one caveat. If you have a variable speed compressor for the heat pump, it's also going to be a much more efficient air conditioner in the summer. So it isn't just heat pumps, it is cooling. So thank you, and I guess we're deferring questions, but thanks very much.
Okay, so we're going to move to question period now. I'm just asking the three speakers to move behind it up to the front where they can be heard by the microphone.
I'll just stand.
And when
I'll
you
stand
ask your
too.
question, we want it to be picked up on the microphone. We have a cordless here, and so I will come around and bring the microphone to you. We're asking this for the live stream, please. So, question over here. Is that on?
Thank you very much for the incredible presentations, tons and tons of awesome info, and happy to be here when it's so cold, talk about this. For the gentleman that just got the heat pump, when you did your blower door test, sir, do you remember how many air changes per hour your house was?
I do not. It's in the report, but I guess I was a bit. We wanted to go through that hoop so we could get the heat pump. So I was kind of. Is there anything unusual? Generally, I think the house was fairly tight. Like,
Okay.
we ranked lower on the tip. Like, we were better than a typical house.
Thank you.
I guess I had a question based on somebody that just talked to me before we came here, and the cost, the basis of it is heat pumps. What is the power requirement? Is it 120, 220? And what is the current? How much current does it take?
They're all over the map. So it depends on the size of the piece of equipment, but think of it, you're going to put a heat pump with a capacity similar to what an air conditioner is. So I'll give you an example for my house. My house right now has a 3-ton air conditioner in it. I'm looking to replace it, and I could probably use about a 3-ton heat pump is just about the right size. So if you can power your air conditioner, you can power your heat pump. Now that's from a breaker size point of view, breaker and wiring. That's usually true. What the difference is the amount of power consumption. So the peak demand for the heat pump it'll probably be less than the air conditioner, because the heat pump's going to be more efficient than the old air conditioner you're taking out. So
I just wanted to make a comment, if any of you haven't had your house audited. We live in a mid-1970s house, and we had it audited about 10 years ago because we wanted to replace our windows and get a high-efficient furnace. And the guy actually had to recalibrate his little gizmo that he uses for the audit because our house was so airtight. And we were shocked. So just because you have an old house doesn't mean it's an impossible thing to deal with. You might be pleasantly surprised.
So I'll give you sort of a scenario, and then based on what I've heard, and you can comment it as well. I live in a 15 or 16-year-old bungalow, high-efficiency gas furnace. I use a natural gas high-efficiency water heater for water heat, and it also pumps radiant heat through the basement floor. I've got solar panels on the roof. So after listening to all this and getting a better appreciation for all the moving pieces and variables, I think the first thing I would do is maybe go shopping for a contractor when I get to that point of inflection of, okay, my forced air furnace is now 16 years old, maybe it's got another 10 years. That would be the point at which I would look at, you know, replacing some sort of furnace and the coil that's in there for the AC with some kind of new solution. Is that, as
I'll take the first point. So one of the, a good rule of thumb in all existing retrofit cases is that unless you're going to get like a huge step up in improvement, you're better to keep what you have now and run it through its whole life, because there's embodied carbon in the device. So like if you had a, say, like a 5-year-old furnace or air conditioner, like definitely do not get rid of it, because it's got a lot of life, and the amount of carbon that you're going to throw away will be more than the amount of carbon you'll save. So from a carbon point of view, the right thing to do is to let your equipment run through its practical service life, and it sounds like that's what you're thinking of, and you're right. Like a furnace or air conditioner, you know, they say 15 to 20 years. It's probably more like 25 years or more, but you'll get to a point where at least say 15 or 20 years out of it, and the time to change is when it's time to do those major upgrades, because then the incremental cost also. I mean, you're thinking of doing like a financial calculation and payback. Well, you're going to pay for a replacement anyways. Might as well pay for the more efficient one, and then your cost increment is small to do it. So did we answer your question?
Do you have a second question?
well, maybe it's a bit more tangential.
Okay.
I drove my electric vehicle here this morning, and the owner's manual tells me there's a heat pump in there. Is there anything that's substantively different in the heat pump in my car than what we've talked about here today?
Heat pump's a heat pump.
Yeah.
Yeah.
When I was looking at EVs, they told us the heat pump was being used to preheat the car, not to actually heat it while you're driving, in their particular model. Maybe it's different.
Yeah.
Yeah.
Just on that, like, we have a plug-in electric hybrid, which has heat pump. If you're running in electric mode, it basically has a cutout of about, I think it's about -10 or -11 Celsius. Again, it's not made for that. I mean, I think a lot of electric vehicles, plug-in electric hybrid, aren't made thinking about a Saskatchewan day like today, but, and then it switches over. In that case, it runs gas to heat, but.
Yeah, thanks guys, great session. Quick question, and maybe it's a two-part question. One is, do you have a forecast more provincially for maybe the adoption rate of this over the next decade or two? And second part to that, where are home builders at with building higher efficiency building stock with this sort of technology built in?
I'll take the first question. There is no data on adoption rate. We anecdotally just think that it will change as market influences happen. It's similar to the adoption of net zero ready homes in the new construction market. So there is some data that's talking about new home construction. So, but that's only a small percentage of the market. You know, like we tell people all the time, 98% of the problem already exists. You know, the new stuff will take care of itself because the codes are getting better, and so anything built, you know, in the future is actually going to not be part of the problem. The problem is already what we have built. So it's the retrofit market. We don't have any data.
Yeah.
We will have to see where public opinion goes, and there's got to be some, like, there's a whole social science side of this that has to come into play. So
It's a bit of a fishing trip, so yeah. Thanks.
yeah.
I will mention too that I've been involved in. I attended there's a course that was specifically for builders. I'm not a builder, but I tended to be part of it. That was put on by the Canadian Home Builders Association, and they're doing sort of a push for net zero ready housing. And actually, my company is helping put on a course for tradespeople at the end of this month in Saskatchewan for passive building principles with Passive House Canada. And so there is more education, more momentum building. I would say we're certainly in Saskatchewan not necessarily on the leading edge of that, but having said that, we also have a long history. If you're familiar with the Saskatchewan Conservation House, which is kind of the basis of some of these really efficient home standards, all that research was done here in the 70s. So we actually have, it's interesting, there are these threads of really super efficient buildings that have been going here for a long time, and now everyone else has caught on and said, wow, this is a great idea, and now we're sort of also catching on and catching up a bit too. So, but it's coming, it's happening.
Matt, I had a question for you. The numbers you ran, you had numbers from 2030 with $170 a ton carbon tax. I don't remember what our carbon tax would have been in January. Do you think, from your gut feel, if we had the carbon tax now, would the heat pump have made financial sense on one of your scenarios?
Yeah, so I did check those as well, and then I figured there was already too many busy slides to show, okay, another scenario, yeah.
Graphs are good.
Yeah, graphs are good, yeah, that's right. It didn't make, it impacted the numbers for sure, but it didn't change the outcome of which was more expensive and which was less expensive. So it is also interesting to see just how much of a price on carbon it takes to counteract the fact that gas is so cheap, right? so that's part of it for sure.
6 times, or somebody said 6 times.
Yeah, it's like 5 to 6 times cheaper than electricity at the moment. Yeah, so.
I have a couple of questions from online. One is, which would be most cost-effective / efficient, a heat pump water heater or an on-demand natural gas water heater?
Somebody reaches for their calculator.
Yeah, I can't do that in my head, but
A lot of moving parts, right?
a lot of moving parts. Like if you're just talking pure efficiency, like at the unit, the heat pump water heater is more efficient, right? Because the natural gas one isn't going to be more than 100% efficient. But if you're talking about the wider, if you're using a grid that's powered by natural gas and then all the losses there, then we're still probably at a point where natural gas is more efficient, especially if you're heating your home with natural gas and then your water heater is stealing heat from your home in the winter. So that's maybe a consideration.
Okay. Another one asks, how much outside space is needed for ground source heating?
That we can't answer that question. Typically, you think in a residential, urban residential setting, you are only going to be able to drill vertical holes. You can have a scenario where you put horizontal loops in. You know, there's a horizontal loop in out at the wastewater treatment plant, but you require acres of land. But they have acres of land there. It was cheaper to go with a horizontal loop. You will necessarily have to do vertical loop, and it's about, I think I've heard that typically it's about 1 ton per vertical loop. So like a typical house would be 2 tons. What
Three-
was it?
three.
3 tons for yours?
3.
Okay, 3 tons, so 3 boreholes. So, and they take, I think roughly, they like to space them out like about, I don't know, I think about 10 meters apart, something like that, or a little less.
I think less.
Yeah.
Yeah.
Yeah. The other thing to think about for a ground source heat pump is if you remember back to my battery analogy, they are an ever declining battery. Okay? So you do have to, coupled with a ground source heat pump, you do need to have a trickle charger of some sort. And a trickle charger in our environment might be solar thermal. So a solar thermal that just bleeds heat into that loop and tries to balance out the amount of energy going into the ground and the amount of energy you're taking out of the ground. So
We had a strange thing when we were buying our house a couple of years ago, is that the lawyers discovered that attached to our title, there were mineral rights for a house in Lakeview. Which seemed, they had never seen it before, and they couldn't imagine why there were mineral rights in a city. But my guess is that probably somebody was looking at putting in geothermal and discovered that they couldn't do it, but they'd arranged the mineral rights already or something like that.
yeah, I have not gone through the process of a residentially zoned property wanting to look at. We've done commercial and institutional projects with boreholes within the city limits, but not a single-family dwelling.
Okay, I'm going to ask one more question here. He asks, our church has multiple zoned furnaces with programmable thermostats. Can a heat pump be integrated with this system, or do we need a heat pump for each furnace?
There are types of heat pump systems that are meant to deal with multiple end devices. So generically referred to as a variable refrigerant system, but you're getting into very specifics about it. There's only a couple manufacturers that make them, but I mean, the other way to look at it is just put a single heat pump, match your heat pump with a furnace. Because right now, if you have air conditioning, it's probably the furnace is matched with a single air conditioner. So you would just take the air conditioner out and you put the single heat pump. So you can do it that way. The variable systems are usually, again, for larger buildings. There's a couple of condos in the city that are built that way. There is one of the hotels was retrofitted in the last 10 years with a system like that. So yeah.
I've often thought about how deep does the coils, how deep in Saskatchewan or northern Alberta, how deep do the in-field cables or coils have to be underground to escape the frost system?
Oh, not far. I mean, they go much deeper on the vertical wells just to get enough length of the well. But I mean, we have this horizontal system that was put out in the wastewater treatment plant. It's like about 8 feet deep. So you want to get to a spot where it's a relatively stable ground temperature, and about 8 feet or so, 2.4 meters deep, it's relatively stable after that.
One last question.
Just regarding the mechanical complexity of a modern-day heat pump versus a gas-fired appliance, who's in front as far as the lower maintenance over the long term?
I would say that the heat pump is no more mechanically or electronically. If you've looked at a modern gas appliance, there's a lot of bits and pieces to make it efficient. So I mean, I think it's probably a wash. It's not like the difference between an internal combustion engine driven car and an electric car where there's, like a marked decreased in the number of components in the vehicle. Like, I don't know, was it 60% less?
2,000 parts down to about
Yeah.
24.
Oh.
I drive an electric car.
Yeah,
so I
like,
go
no,
by-
it's not the difference. The difference might mean, whether or not there's 80 parts versus 70 parts, or, like, they both have a relatively...
If I can sort of just pick up on what Tom's saying is, I think the core elements they're relatively simple and direct. The control electronics, the other sensors that get the efficiency up on both sides are equally complex, and the reliability is more so the availability of replacement parts and the support. Like, that's where, if you're sort of looking for is one going to break down more than the other, they're equal. It's then the difference between it being I've got to replace a whole system, or I just need a repair call, is more, are they current in terms of parts stock?
So more importantly, and Matt and I were talking about this the other day, one of the reasons that right now we are, I am, and I think Matt is, quite lukewarm on the natural gas heat pumps is I haven't seen that there is a maintenance network in the province that could actually service them. I mean, we put in some gas-fired chillers back in the 90s because the gas rates were so cheap, like it made more sense to put gas-fired chillers in. We ended up taking them out a few years later because the servicing costs were just so horrendously high. We had one client that to get their chiller service, they had to bring in a service technician from Toronto every time. Like, it makes no sense. Whereas, an electrically driven chiller, you could, here in Regina, you could get somebody. I would say that's the same position as a heat pump. You want to make sure you're putting in a piece of equipment that needs to maintain, will have problems. I mean, all mechanical things break. That's an axiom that's true. And so they do need to be serviced, they do need to be maintained, and so you need a service network that can do it. And in the electrically driven heat pumps, be they water or air, there's a service network already in place.
You might not be able to do this, but is there particular brands or designs of systems that you might give the gold star?
No, take the grant out of it. There's actually way more products available that are from reliable and very efficient that aren't necessarily on the grant list. And as I found out, that's because to get on the grant list, it's up to the manufacturers to do all this testing to comply with the granting agency's requirements. So it's a foible of the granting system. But there's some super efficient. Matt mentions the Mitsubishi product. I don't think there's a better one than the Mitsubishi one in terms of cold climate and efficient right now. But there's lots of manufacturers that are making a lot of progress. Lennox, Trane, American Standard. I guess Trane and American Standard is the same thing. LG, like, list goes on.
So I guess we need to bring this to an end. I have one last question. It's the question that actually, as we began talking about this in Kairos Regina, we thought maybe we should do something about this. We heard Scott Moe say heat pumps don't work in Saskatchewan. What do you want to say to Scott?
About heat pumps.
Heat pumps work in Saskatchewan.
They work?
It's like we said, I think our first slides were both Matt and I mean, and they've worked since the 1970s.
Very good.
Thank you for coming out.
Well, thanks again for all of you for coming, and I'd like to thank our three presenters. Oh my gosh, you guys, your knowledge, your experience, your generously sharing of your time today, and I think we've all learned a lot, and I think hopefully we're going away with some questions, and we'll continue to do a little research on and spread the word. So thanks again for coming, and just to let you know that Kairos Regina has set up a YouTube channel, and signing up your email list, we'll be sending out the information about how to get access to that. And again, feel free to share with your friends, because if people aren't interested now, they will be. So thanks again for coming, and stay warm.